I will start the recording. Okay. Anyway, the thing is recording and all this ruckus to put it on YouTube. So, okay. Sorry about that. Sorry about that. Okay. So let's continue before we were rudely interrupted with okay. I'm just gonna, go to the sliding filament theory that let me just see. That's way too long. Okay. A lot of ads. I just want to show you a quick, maybe this is good. Okay.
So episode 43, I'm going to go into the details of muscle contraction. This is going to be the last video in the muscle contraction series, so enjoy. Let's get right into it. Now, you can always go back to episode 42 to refresh your memory, but we said that the functional unit of contraction is called the sarcomere, and that is what we're looking at right now. This unit is one sarcomere. And we said that we had a thick filament that was called myosin, and we have a thin filament that is called actin. And we said that when muscle contraction happens, the motor neuron releases neurotransmitter that stimulates calcium release. And when that happens, the fibers slide against each other, just like this. So as the muscle fibers become shorter, that is the muscle contracting. And you can clearly see that in this animation. Now, the reason we said that this can happen is because on the myosin filaments, we have these heads, and those heads extend and bind to the actin. And when they bind, they kind of flex. So it moves in this direction, and that pulls the actin, shortening the sarcomere. So what we're going to do today is we're going to look at the details of what is happening there. So we're going to look at the 6 steps in muscle contraction. And this is another image that's showing something similar to what we've looked at. We have the myosin heads. Let me do that in a different color so that you can make sure to see it, because we have a lot of red there. So we have the myosin heads that are binding to the actin filaments. Now, here we're going to be looking at that in more detail. So we have the actin. Yes, it's a different spelling because it's from a different language. But on the actin filaments, there are 2 things that are very important. We have tropomyosin, as you see here. So that's this long strand here. And on top of the tropomyosin, we have troponin. And this is a complex that we find all along the actin filaments. Now, here's the situation. Because this is here, the myosin heads want to bind to the actin. There's some binding sites on the actin. So let's say this is a binding site right here. But what's the problem? The tropomyosin is covering that binding site, so the myosin heads cannot bind. Okay, so we have these myosin head binding sites all along the actin. Myosin heads want to bind. We have all these myosin heads ready to do their business, but they cannot because it's blocked by the tropomyosin. All right, so let's go now and look at the 6 steps of muscle contraction. Step number 1, calcium is released from the terminal cisternae. Remember we said that the terminal cisternae is a part of the sarcoplasmic reticulum, and that is where calcium is stored. So calcium is released. You can see here we have this little binding site for the calcium. So the calcium now comes and binds to the troponin. So here we have calcium in binding to the troponin. And then what that does is it causes a conformational change. To put it more simply, we're just moving the tropomyosin troponin complex. So that moves, and when that moves, it exposes the binding sites on the actin. That's step number 1. So step number 1, we had calcium in the terminal cisternae. That is released when there's a stimulus. The calcium ions bind to the troponin, causing a conformational change in the troponin tropomyosin complex. In other words, it's moving out of the way. And then the next step can happen. And that step is the myosin heads can bind to the binding sites on the actin. So this is one binding site. And for simplification, we're just showing one myosin head. But as you know, we have many myosin heads all along this actin. Now, in order for that to happen, we said that there's normally ATP that's on the myosin heads, and you saw that in the previous figure, but that ATP has to be hydrolyzed to become ADP and an inorganic phosphate. So we have ADP and the phosphate. All right, so we have the myosin head that has bound to the binding site on the actin. That was step number 2. Step number 3, this ADP and inorganic phosphate is released from the myosin head. I'm not showing that in the figure, but just imagine that being released. When that is released, it causes the power stroke. In other words, it causes this guy here to flex. And when it flexes, it moves in this direction, and that causes the actin to slide across the myosin. Okay, so calcium is released. Step number 1, binds to the troponin, causes this change in the troponin tropomyosin complex so that it gets out of the way. ATP being hydrolyzed into ADP and inorganic phosphate is the state that this needs to be in for the myosin head to bind. When those are released, the myosin head flexes and we get the power stroke. That's step number 3. Let's go to step number 4. Step number 4 is another one that I'm not showing, but we have ATP. So this is an ATP molecule that comes in and binds to the myosin head. When that binds to the myosin head then detaches from the actin, so we no longer have that connection. That's step number 4. Step number 5, ATP is hydrolyzed, which re-energizes the myosin head. So once we have ATP being hydrolyzed, like it is here, that re-energizes the myosin head, and it's ready to go again. One more step, step number 6. This calcium here needs to be gone. So we have the terminal cisternae, and it's not shown here. So I'm just going to draw it with my great artistic skills. And we have calcium pumps in the terminal cisternae. And what that does is it basically pumps that calcium back in.
All right, everybody, I just want to say that he does a little bit of a job where he can show some more visuals. And there is an animation that I really like about the muscle contraction process. I will show it to you.
You use muscles every day. This woman is using muscles to breathe, circulate blood, and move her hand to take notes. Your cardiac and smooth muscle tissues are involuntary. You do not consciously control their actions. Skeletal muscle works under voluntary control. Skeletal muscles are composed of bundles of muscle fibers. Muscle fibers are long cylindrical cells containing several nuclei. Muscles will contract or relax when they receive signals from the nervous system. A neuromuscular junction is the site of the signal exchange. This is where the synaptic bulb of an axon terminal and muscle fiber connect. Muscle fibers are composed of many myofibrils. A myofibril contains contractile units called sarcomeres. Sarcomeres run adjacent to one another down the length of the myofibril. Each sarcomere consists of alternating thick and thin protein filaments, giving skeletal muscle its striated appearance. The muscle contracts when these filaments slide past each other. The thick filaments are myosin, which are anchored at the center of the sarcomere, called the M line. The thin filaments are composed of the protein actin, which are anchored to the Z lines on the outer edges of the sarcomere. Because the actin filaments are anchored to the Z lines, the sarcomere shortens from both sides when actin filaments slide along the myosin filaments. Although the action between the filaments is described as sliding, the myosin filament actually pulls the actin along its length. The cross bridges of the myosin filaments attach to the actin filaments and exert force on them to move. This action is known as the sliding filament mechanism of muscle contraction. In this model, the sarcomeres shorten without the thick or thin filaments changing in length. A contraction begins when a bound ATP is hydrolyzed to ADP and inorganic phosphate. This causes the myosin head to extend and can attach to a binding site on actin, forming a cross bridge. An action called the power stroke is triggered, allowing myosin to pull the actin filament toward the M line, thereby shortening the sarcomere. ADP and inorganic phosphate are released during the power stroke. The myosin remains attached to actin until a new molecule of ATP binds, freeing the myosin to either go through another cycle of binding and more contraction or remain unattached to allow the muscle to relax. Muscle contractions are controlled by the actions of calcium. The thin actin filaments are associated with regulatory proteins called troponin and tropomyosin. When a muscle is relaxed, tropomyosin blocks the cross-bridge binding sites on actin. When calcium ion levels are high enough and ATP is present, calcium ions bind to the troponin, which displaces tropomyosin, exposing the myosin binding sites on actin. This allows myosin to attach to a binding site on actin, forming a cross bridge. Calcium ions are stored in the sarcoplasmic reticulum and are released in response to signals from the nervous system to contract. Neurotransmitter molecules are released from a neuron and bind to receptors, which depolarizes the membrane of the muscle fiber.
Okay, ladies and gentlemen, thanks for your attention with the overview. I got some chat messages. Let me just say I want you to follow what we went over in our notes, okay? The visuals are meant to help you. Other teachers teach it in a different way, but these visuals are meant to help you. I wanted you to mainly to see what you just saw, that the actin and myosin come together, the myosin head swivel. Ladies and gentlemen, you have to see it. You have to, you can visualize it with your hand swiveling, but seeing the little cartoon is nice of the sliding filament theories. And that's why I took the time out to do this. We'll continue with questions at the end. Let's march on. We've discussed that calcium has to remove and therefore relax the muscles. One thing that happens during rigor mortis, which is death after, which is stiffening of your muscles after you die, about 4 to 6 hours later, is that your tissues remain on, how do I put it? Your tissues get stiffened. Why do your tissues get stiffened? Because your muscles deteriorate after you die. And calcium literally leaks into the muscle, causing the sliding filament contraction that we just talked about. So that's how you get stiffened. How come the individual doesn't relax? They don't relax because it takes ATP. The last step of the sliding filament theory is relaxation. It takes ATP to unbind the actin and myosin and allow the muscle to relax. So I have a story from way back. When I was a kid, my aunt died, and I remember sitting in the funeral parlor. No one was there. One of my favorite aunts, Tunty Pally was her name, favorite aunt, 1977. And she was buried very quickly. She was very old, in the 90s, and not a lot of people around. And I remember her moving in the coffin. I mean, I didn't know about rigor mortis, that it stiffens you. And I saw the poofy dress move, and I ran the heck out of there. Never been the same since, I tell you that. But to make a long story short, that is rigor mortis. Rigor mortis is, and it's a weird thought, it really emphasizes that you need ATP in order to relax the muscles. And that's kind of why I tell the story, because it is all a sliding filament theory. It is all biology. You almost don't even have to be alive for it. It's just the way that myosin and actin slide together. And of course, you need ATP to be alive. You have ATP, and you need ATP to relax your muscles. We're going to talk now a little bit about muscle activity, and we're going over a little bit over our 10 o'clock hour because of the electrical disturbance at my house. Anyway, the electricity's back on. Who knows why? 1 minute, it just knocks you out then. Muscle and exercise. Let's talk about the difference between an isotonic versus isometric contraction, and then we're going to have a little bit of a competition. All right, and we'll all, if you want to compete, you got to go on. You got to show your image, and whoever wins the competition, usually in class, I give them a point. But let's see how it works here. Okay, first, before we do our competition, you got to understand the difference between isotonic, isometric. This competition shows you how important isometrics are. Isometric contractions mean you don't change, you don't move something, you don't move the muscle you don't move a load as the muscle contracts. So its definition is muscle does not change shape with the load. So if you do a squat or put your hand on your forehead and push your forehead into your hand. All right, let me show you myself. Push your forehead into your hand. That's an isometric. You're strengthening your neck muscles. Now put your hand in the back, push back. You're not moving a load, right? Your head's not moving. You're keeping it stationary, but you're changing the muscle shape, right? You are putting tension on the muscle. That's an isometric. In other words, nothing moves with isometric. You tense the muscle, nothing moves, that's an isometric. You tense the muscle and something moves, that's an isotonic, right? So if I move my arm, right, you move your head this way. That's an isotonic contraction. So that's the difference between isometric, isotonic. Isotonic, a load moves. Isometric, a load does not move. And isotonic can be divided into concentric and eccentric. Concentric means the muscle shortens, so a curl up like this is a concentric muscle contraction. And then strengthening or lengthening the muscle, so a curl down for your biceps would be an eccentric contraction. And when all these things happen, there's a lot of metabolism that's happening, right? You've got 3 steps in getting the energy out to make a muscle move. A creatine phosphate process, and an anaerobic respiration process, and an aerobic respiration process. Let's go over these 3. Creatine phosphate gives you energy from creatine phosphate for the first 10 to 15 seconds of an activity. It's like instant phosphate energy. The next phase is to get energy from sugar quickly. Just break it down in half. That's known as anaerobic respiration. It happens without oxygen. Then after that, when oxygen is present in your muscles, it's called aerobic respiration. Aerobic respiration means you're using oxygen to break down sugar to get energy. And that's where you get the bulk of your energy, through aerobic respiration. When a muscle fatigues, it means it doesn't have enough ATP. You deplete your oxygen, glycogen, and lactic acid is a byproduct that builds up after exercise. And that's what kind of gives you the burning, hurting feeling. A myogram shows you how muscle contracts. And a myogram is a procedure whereby you put a little hook on a muscle, an electrode contracts it, and you see how much it pulls and how quickly it contracts. There's 4 phases. There's a latent period, which is, the word latent means nothing's happening. So nothing's happening because it takes time for the muscles to, all these chemicals to move, for the muscle to contract. Then there's a contraction, so the tension goes up. There's a relaxation, the tension goes down, and then there's a latent period. Nothing happens. And we say that there's 2 curves, a fast curve and a slow curve. The fast curve of a myogram means it's a fast twitch muscle. So blink your eyes. That extraocular muscle of your eye is fast twitch. That means it happens fast. The x-axis is time. It happens fast. The other type of muscle is a slow twitch muscle. That means it takes longer to contract and longer to fatigue. So the soleus muscle is a muscle in the back of your calf, and that takes a longer time to fatigue. So if the curve is flatter, that means the muscle contracts longer. If the curve is short, like this first one, the muscle contracts a lot faster, all right? So the eye and the leg are examples. And we have a different proportion of muscle fibers, okay? Slow, fast twitch is throughout our body. We all have different amounts. Again, slow twitch fibers are very fatigue resistant. Marathon runners have a lot of slow twitch fibers. Figure 14.27 kind of talks about the different types of fibers in different people. We have 2 types of fast oxidative and fast type fibers. One is fast oxidative, one is fast glycolytic. Fast oxidative means it is intermediate to fatigue. So if you're a sprinter or you like to do some fast walking, you have a lot more fast oxidative fibers. Those are the fibers that will become more active. Fast glycolytic is an intense activity. Like if you do a rapid weight bench push, or you hit a softball, you hit a ball. In other words, an intense activity tends to use more fast glycolytic fibers. A sprinting type activity, a little longer, right? A little longer to fatigue. That's fast oxidative, and very long to fatigue, like posture muscles or marathon running. That all requires more slow oxidative. So those are the 3 types of muscle fibers. And feel free to ask questions at the end. I've got the effects of exercise. We talked a lot about exercise, right? But one thing I want to mention is you can never increase the number of muscle cells you have, all right? Number 5, you do not ever increase the number of cells you've got. You're born with 100 cells in a muscle. I mean, more than that. Let's say 1 million cells in a muscle. That's all you're going to get. The effect of exercise is to increase the muscle size, to hypertrophy it, to increase the vessels around it, or the vascularization around it, to increase the number of mitochondria, or to increase the satellite muscle cells. All of those are what exercise does. It makes the muscle more efficient, but does not increase the number of muscle cells that you've got. Okay, I just want to make that clear. A couple of terms for you to know before we're done with the lecture. Myalgia is equal to muscle pain, right? That's a word for muscle pain. Flaccid means you have less than normal tone, and tone means you remain contracted even in a relaxed state. So again, let me repeat. If you hear the word myalgia, that means muscle pain. A lot of medications can cause myalgia or muscle pain. Fibromyalgia means widespread muscle pain, we believe due to nerves being overactive. If something's flaccid, that means it is weak or flabby, you could say. The muscle is just not toned as much as it should be. And tone means it's in a relaxed state, it remains contracted. We can do a little activity if you want. I'm not gonna, I can't give points for it, but you can do it on your own. Usually I do this competition. I'll show you a picture. Here's what you gotta do. All right, so it's a wall sit. Let's go back to isometrics. I often do against the wall. Let me see if you can see this. So against the wall, all right, go down and just sit. And try it as long as you can. It's called a wall sit, and your legs will start feeling it right away. That's an isometric contraction. And I have you do this. If you want to do it with me right now, you can. I'm not going to do it long because I'm terrible at it. Your quadricep muscles are really holding you up. And what it does is, at first 15 seconds that I've been doing this, right, your creatine works. Then you're going to start seeing ATP come from your anaerobic respiration. There's not oxygen ready. Then you're going to start putting oxygen to it. And then the muscle is going to start having pain and fatigue, and I'm done with it already because it hurts. When I do the competition in class, I always lose, all right? And the person who can do that the longest, I give a couple of points to. I can't kind of do that now because I can't see you guys, and it's kind of too awkward. I was going to do it, but I think, whew, I'm out of breath. So what does that show? Anaerobic respiration. I'm out of breath. Even from that, you know, my quads are not, you know, really as strong as they should be. I walk a lot, but, you know, we all have different musculature. I am not great at wall sits. You can practice it. Build yourself up. The purpose of that activity is to show you how strong an isometric is. You do that for 2 minutes, you'll start breathing heavy and your legs will start burning. If you are doing it right now, you know what I'm talking about. And you need aerobic respiration to come in and bring the oxygen. It shows the power of an isometric contraction, how much it builds your muscle. So a lot of guys, they think you got to keep pumping iron and moving things. Isometrics work very well as well. All right. And that concludes the lecture. I want to shut off the recording, and then we can talk questions.